We are in section 13.2 and just need to finish up the notes from that section. So in class I went over this example 1 and I just want to recap it. When we have a vector function, r of t, given in this vector form, and we want to, as in part A, sketch the plane curve, which is, you can think of it as a space curve in 3D. It's just a line. It could be a helix. It could be be traced out in a three-dimensional world, but it is just a parametric equation of a line in 3D. So the plane curve is that line without the arrows, and it turns out to graph it, you could plot for t equals 1, for example, and write out what the point would be, and that would be e to the 0, which is 1, and e to the negative 0, which is 1. So it would be 1, 1. And that point is on this graph here. However, getting the kind of this nice exact curvature and whatnot is a little bit harder to do, and plotting points is kind of a good backup plan. But when we learned parametric graphs and parametric equations back in a previous calculus course, it turns out eliminating the parameter t is kind of a good way to get a graph that you can just graph. So in order to do that, you look at the equations for our parametric equations, x equals e to the t and y equals e to the negative t, and try to relate those and put it just in terms of x and y because it's a two-dimensional curve. And so when you do that, you can note that y is 1 over e to the t, which is simply just x. And so to put them together and eliminate the parameter, it's y equals 1 over x. And so here it only makes sense to have the positive x, so that graph is this. That was just to get a graph, so it's not really intuitive that you'd want to do all that work, but in general that's a better method. Part B, find the derivative, is pretty easy. You just look at the derivative with respect to t of both, each component separately. So the derivative of e to the negative t, use the chain rule. You get e to the g of t up. Take the derivative of g of t, which you get negative 1, and then you get that result. Derivative e to the t is e to the t. And then finally C, here sketch the graph of the vector function r of t and the tangent vector r prime of t for t equals 0. So to get what those vectors would be, you simply just plug in t equals 0 into each of those equations you found or were given. So one is a vector 1, 1, the other one is a vector 1, negative 1. So writing their appropriate labels here, when you draw the graph of the vector for the vector function evaluated 0, it better be a point on your space curve or the plane curve, otherwise there's a mistake there. And so notice that this blue here is going from the origin to a point on that curve. The way that we typically draw the vector representing the derivative is we draw it at that point and from this point that is on the graph, so at 1, 1 in this case. So 1, negative 1 from that is representing our vector that's on the tangent line. So that's another thing that should match up, your understanding of what the tangent line would look like here, and the vector, tangent vector, should be on there as well, or the derivative at that point. So moving on, we need to talk about something called the unit tangent vector. So it's given special notation that it's a vector t, capital T of t, and again it's the unit vector. Unit tangent vector is just as it sounds, it's just a unit vector representation of a vector function's derivative. So in other words, just like you would imagine, r prime of t over the magnitude of r prime of t. So this vector here representing the tangent vector is not going to necessarily have a length of 1. And so all this does to it is it makes it have a magnitude of 1. And that's helpful because a lot of times we actually don't care about the magnitude of the tangent vector, we just care about the direction and that tangent line. And so it gives a nice visual too to just have that all be a magnitude of 1 for that vector. and it's used in a lot of different things, as we're going to see in the next section. Anyway, that's the equation. I believe that I say that I give that to you. To be determined, I guess, but I'm pretty sure I just give that to you. I'll give that to you on the formula sheet. Alright, example 2. Find the parametric equations for the tangent line to the curve. R of t is cosine t in the I, sine t in the j, and t in the k. At the point 0, 1, pi over 2. So recall here that a line, in this case a tangent line, is in this vector form, if we want to do that. So here specifically this R notation is not the vector function, but talking about like what was just our general vector equation of the line in 3D. Okay, here is what it was. It was R is equal to R naught plus VT. So what we can think of here for the tangent line is this a straight line, so it means it's of this form. And we have our R naught automatically because we got a point that we just basically vectorize. And now what we are needing here is V, which is a vector in the same direction of the line. So because we're trying to find the equation of the tangent line, that's specifically going to be R prime. We're a little confusing here. I should use of t here to be clear that I'm talking about the, oh shucks, look what I just did. Somehow I changed the order of all these answers I was going to reveal. Oh well. So this was of the vector function, derivative vector function. So that's kind of like your slope in this vector form of the line. Alright, no mystery here on what these are, so we find the derivative very easy component by component. And now just like when we took derivatives in Calc 1, we need to determine what we plug in here, because it says at this specific point. Usually we would plug in like the x value or something like that, but here we have it in terms of t. So it's a little bit of a stumbling block, but if you note that you just relate each of the components with their point, it's actually pretty obvious a lot of times what t has to be for that point. So notice the first component, or the x component, is cosine t, second is sine t, and then our z is t. So when we're given this point for this specific vector function, we're just being told that t is pi over 2. So it's not actually a mystery anymore now. And we can go ahead and plug in that t in our R prime function of t to figure out what that derivative is. So we do that and we get negative I plus k. And now putting in an general equation of a line, what we have for a tangent line is we have our R naught, which is the point written as a vector. We put in our tangent vector at pi over 2, and we're pretty much done there. It asks for the parametric equation, so we just go ahead and break it up into, remember this is x, y, z, and so x is 0 plus negative t, got that, y equals 1 plus 0 times t, okay, so on and so forth. So this example is actually one from the 13.1 notes. We got this really beautiful image displaying the space curve. It's a helix. And I could plot a tangent line on here to illustrate what this tangent line looks like in 3D and hopefully have you understand that. So you're not going to have to actually do this by hand, but I have the point 0, 1, negative, or pi over 2. And then what we just found was the parametric equations of the tangent line. And so it's just a line and in vector form. So one thing you can do is just, you know, this was for t equals pi over 2. If I let t equal something else, I can get another point to draw a line. And so we can appreciate that when we have this coil here, that the tangent line in 3D would be in this orientation. I put the differentiation rules in here not to really even call any attention to it other than, because we're not going to use them right now, just to kind of be aware and look. But one really interesting thing is because we have different kinds of multiplication with vectors, we actually had 3 variations of the product rule. So for, maybe we'll use these later, but for now I just wanted to say, hey, that's cool. And now we can move on. Integrals. Integrals are just as easy as derivatives. What we get here for our vector function is we just get taking the integral component by component if we want to find the integral overall of the vector function. So doing well, not actually doing an example, but revealing an example, I guess. These aren't really doing anything. Is when we evaluate a vector function's integral, just break it into each component. That's what I'm showing here. Do the integral of t to the 1/3 with respect to t is 3/4 t to the 4/3, and then fundamental theorem of calculus part 2, we're going to plug in there a 1 minus a 0 plugged in. The integral 1 over t plus 1 is a natural log of t plus 1. Easy substitution there. That doesn't really come into play, but moving on. E to the negative t, the integral of that is negative e to the negative t. Plug it in, do the work there, and we get our integral. So that was a definite integral where we have little numbers next to the integral sign. What if we have what's called an indefinite integral? We're going to do this the same way, component by component. One little twist here is when we don't have the numbers, then we usually just put a plus c at the end. Turns out we do the same in vector land, but just call out that when we write the plus c, it is a vector in this context. It's an arbitrary vector. And the answer to an indefinite integral of a vector function is a family of vector functions. And we call it a family because of the plus c at the end, just like if we were just talking about a real valued integral problem, integrating there, we would have the plus c as a constant. We'd be talking about a family of functions because of the plus c would shift it up or down. Here it's going to be shifted by some vector there. And that's it for this section.